Well, hello again, pre-calc students. It's that time again, math time. Today we're going to do section 3.7 of AP Calculus. It's called implicit differentiation. It's a really fancy term for saying you're going to find the derivatives of things that may or may not be functions. So often, equations are written in more than one variable. Well, I should say more than two variables. Sometimes there's z's and even scarier things like that. But for the purposes of our implicit differentiation, we're just going to talk about things that are written in terms of x and y. But when y cannot be isolated, you can't get y by itself. Like this one here. It doesn't matter what you do to this thing. Trust me, I've tried. You cannot get y all by itself. It's just not possible. Does that mean we can't find the derivative, aka the slopes? Of course it doesn't mean that. You know there's a way, otherwise I wouldn't have, had these notes. So when a function is defined in a manner like this, or any one where you can't get y by itself, we still need to have a way to find that derivative. And the way we do this is by treating y as a differentiable function of x, and then we use the chain rule. We call this implicit differentiation. So you're like, what? What do you mean you use y as a differentiable function of x? Well, how about this? If I told you that y was some function in terms of x, you should be able to find the derivative of this. You see, that means find the derivative of both sides. So you would say that the derivative with respect to x of y is dy dx. And the derivative of the right side would have just been f prime of x. So what we're going to do is we're going to pretend that y is equal to some function in terms of x. Okay? All right. So let's dive right into it. We're going to find the derivative of both sides of this. So we're going to write it like this. D dx of y squared equals x. D dx means the derivative with respect to x. So the way we're going to do this is we're going to pretend that y is some function in terms of x. You're thinking that y is, I don't know, some stuff raised to the second power. And there's x's in here, okay? That's what you're looking at. And you go, okay, if there was a function in terms of x right here, then in order to find the derivative of the outside, what I would have to do is bring this 2 down to the front. I would not touch the inside. And now remember, the inside is some function in terms of x. Since we don't know what that function in terms of x is, we're just going to call it y. And now we get to multiply by the derivative of the inside. Well, what is the derivative of y? Oh, it's dy dx. And on the right side, the derivative of x with respect to x means, well, just use derivatives the way that you're used to, so it's just 1. Your job was to find dy dx. So if you want to get dy dx by itself, you just divide both sides by 2y. So dy dx is 1 over 2y. And there you have it. That's it. Basically, any time that you're forced to take the derivative of a y, you call that dy dx. This one says find the slope of this circle. Oh, you can't see what I'm pointing at. This one says find the slope of the circle at this point. So we know this point is on the circle, but we don't know what the slope is there. You see, I have an x and a y. So when I find my derivative, I'm going to plug in what I'm allowed to, where I'm allowed to. Like, see, for this one, if you were trying to tell me what the slope was, the derivative, you actually had to do it in terms of y's. Okay, so we're going to find the derivative with respect to x. We're going to do d dx of the equation x squared plus y squared equals 25. All right, so the derivative of x squared. it's going to follow the rules that we're used to because we're taking the derivative with respect to x. So we bring the 2 to the front, drop the exponent by 1. Boom, done. Plus, some function in terms of x. It can be thought of being as inside, like that. So we bring the 2 down to the front, we don't touch the inside, then we multiply by the derivative of the inside. And the derivative of y is dy dx. And the derivative of every constant is 0. Now all we have to do is get dy dx by itself. So I'm going to say 2y dy dx equals negative 2x, and then I'll divide both sides by 2y. Dy dx equals negative 2x over 2y, which simplifies to negative x over y. So if you want to know the slope at this point, you plug in 3 for x and negative 4 for y, and we get that the slope is negative 3 over negative 4, which is just positive 3/4. There you go. So the slope of the circle at this point is 3/4. Interesting. All right. This one says, show that the slope, dy dx, meaning the derivative, is defined at every point on the graph. What that means is we have to show that there are no discontinuities in the derivative. Okay, so let's go ahead and tackle it. Oops, we're finding dx of our equation. Now I can't call it a function because it might not be a function. I mean that one at the very, very top, the x cubed plus y cubed minus 9xy equals 0. You should go to Desmos, type it in, see what you get. In fact, I would go to Desmos for all these and type them in just because I'm a big fat nerd and I'm really, really curious about things. Alrighty, right here, finding the derivative with respect to x. Now remember, constants just come along for the ride. And then we say, what is the derivative of y? It's dy dx equals, the derivative of x squared is just 2x plus, okay, here we're going to have a chain rule. The derivative of a sign thing is always done the same way. It's the derivative of the outside, which is going to be cosine. Don't touch the inside. Then we get to multiply by the derivative of the inside. There. At this point, we know we're trying to get dy dx by itself. So what that means is you're going to have to get everything that has a dy dx to the same side. I'm going to go ahead and subtract this term from both sides. And now, in order to get dy dx by itself, we just factor it out as a GCF. Okay, isolate dy dx by division. Running low on space. Let's see. So 2x divided by 2 minus cosine y. All right, so our derivative is a fraction. That means the only places where we would have discontinuities is if the bottom equals 0. Okay, so you go, all right, let's see. 2 minus cosine of y equals 0. Add cosine of y to both sides. You get cosine of y equals 2. And you know what? That's just plain impossible. Why is that impossible? Because the largest value that a cosine can reach is 1, unless the amplitude has been changed. So since the cosine of y can never be equal to 2, this derivative is always defined. Ta-da! Okay. Flip them over. 2 more to go, and we'll call it quits. Ooh, tangents and normals. Find the tangent and the normal to this ellipse. Now, we did some ellipses earlier in the year. If you graph this ellipse, I think you'll find it kind of interesting. Spoiler alert. It's diagonal. Ooh. Okay, so we are going to find the tangent and the normal to this thing at this point. That means we're going to have to find the derivative. All right, derivative here, standard 2x minus, oh boy, this is x times y. This is actually going to be a product rule. Okay, so I'll do that over here. U is x, v is y, u prime is 1, and v prime is dy dx. U prime v plus uv prime. So I'm going to wrap that inside parentheses, parentheses. Actually, let me make that a bracket. Parentheses. U prime v plus u v prime close parentheses. See, this minus sign is going to get distributed to both things there. Now we're finding the derivative of 2y. That's going to require our chain rule. Bring the 2 down to the front, and now take the derivative of the quote-unquote inside. That's going to be dy dx. And the derivative of this constant here is 0. Distributing my negative sign and cleaning this up, I get 2x minus y minus x dy dx plus 2y dy dx equals 0. Okay, time to isolate dy dx. And it doesn't really matter which side I move it to, but I got this weird thing about where I just like the x's to be positive, so I'm going to move these two terms, the dy dx, to the right. It's going to give me a 2x minus y equals x dy dx minus 2y dy dx. Now over here, I can factor dy dx as a GCF and divide. There you go. Divide both sides by x minus 2y, and you have your derivative. Oh, believe it or not, we are not finished. Now that we've found our derivative, we look back to the top and read the directions and go, oh yeah, that's right. I'm trying to find the equation of the tangent and the normal. So I have to plug in x is -1 and y is 2. So m of our tangent line is equal to 2 times the x value -1 minus the y value of 2. That's just me plugging in -1 comma 2 over -1 minus 2 times 2. It gives me -2 minus 2 over -1 minus 4, or -4 over -5. I think I can squeeze it in there. It's going to give me 4/5. So my tangent slope is 4/5, and my normal slope, also called the perpendicular slope, will be the opposite reciprocal, or -5/4. So tangent is going to be y minus 2 equals 4/5 times x plus 1, because it's minus -1, and the normal will be the exact same stuff except for -5/4 right here. Ta-da! Done. And last but certainly not least, because it's gonna be a doozy, we are going to find the second derivative. That's right, we're going to find the derivative of the derivative, and it's going to happen using implicit differentiation. So let's go ahead and dive right in. Dy dx of 2x to the third minus 3y squared equals 8. The first derivative is pretty simple. Not much going on here. A standard derivative here, bring the 3 down to the front. It's going to give us 6x squared minus, chain rule, bring the 2 down to the front, 6y, which is the inside. We didn't touch the inside now, times the derivative of the inside, which is dy dx. Because remember, we're treating y as a function, so it is an inside, equals 0. All right, let's get dy dx by itself. Moving this term to the right is going to give me, and if you'll excuse me, I know I'm flipping it on you, but That's just because I wanted dy dx by itself on the left. And then dividing both sides by 6y gets me dy dx equals 6x squared over 6y, and the 6's cancel, leaving me x squared over y. Awesome. The second derivative is going to be the derivative of this thing. That's right, the quotient rule with implicit differentiation. Yeah, buddy. So we have to find d dx of x squared over y. All right. Well, like I already said, we're going to have to use the quotient rule. So u is x squared and v is y. Then u prime is 2x and v prime is dy dx. Let's see, can I squeeze my quotient rule right here? I can. U prime v minus uv prime all over v squared. I always write it. Let's fill it out. Strange structure here, but this is how we denote the second derivative. Equals. Let's start filling it out. And I'm going to do it without parentheses, just because they're not really going to be necessary. U prime v gives us 2xy minus u v prime all over v squared. See, the parentheses didn't really do us any good there. And we're looking at that and going, but how is that useful? Our second derivative has a first derivative symbol in it. And I wait a minute. I know what dy dx equals. It equals x squared over y. So I can substitute this x squared over y right here. Well, since this x squared is not in the bottom of the fraction, it's actually being multiplied to the top of the fraction right there. And I'm going to go ahead and write the 2xy as a fraction as well, because the best way to do that is to find a common denominator. That is really the best way to clean this up. I think it's pretty obvious that the common denominator between these two things is y. So I'm going to multiply the top and the bottom by a y. There's already a y on the top, so boom, like that. This is going to clean up to 2xy squared minus x to the fourth over y. And then you're dividing by y squared. But remember, dividing by y squared is the same as multiplying by its reciprocal. So I got a little tight on space down here, but the final, most simplified way to write this is going to be d squared y dx squared equals, we combine this to one fraction, 2x y squared minus x to the fourth over y to the third. And you know what? I'm actually going to separate it into two different fractions just because it would make plugging in x's and y's easier. So when we separate this thing, they're both being divided by y to the third. So I have 2xy squared over y to the third minus x to the fourth over y to the third. And I'm having to write smaller and smaller and smaller. I'm going to have to squeeze my answer in right here. But right here, these two y's take off 2 from the bottom, and you're left with that. So it is much easier to write it as 2x over y minus x to the fourth over y to the third. Whew! There it is. An exercise in mental fortitude. I hope you didn't quit on me. If you have any questions, hit me up on Zoom. And if not, you'll be hearing from me again on the next set of notes. Have a good day, everybody.